So the octet rule, this is continuing on with electron configurations. The octet rule states that electrons atoms need 8 valence electrons in order to achieve maximum stability. So in order to do this, they're going to gain, lose, or share electrons. This is kind of an introduction into bonding, which we're going to be getting into more next unit. But for right now, we're going to be focusing on gaining or losing. So looking at the valence configuration for oxygen, would just have the 2s2, 2p4, which would give us 6 valence electrons. In order to have 8 valence electrons, we would need to gain 2 electrons in order to achieve maximum stability. So that would give us 2s2, 2p6. So we now have a full valence energy level. But with those 2 electrons, it's going to result in a charge of -2. So now instead of having an atom, we have an ion, and the ion formed is O-2. Elements want to be like the noble gas family because they have the most stable electron configuration that requires the lowest amount of energy. So they're going to gain or lose electrons. So when we gain or lose electrons, it ends up being an ion with a So an ion with a positive charge is a cation, and an ion with a negative charge is an anion. So these are just terms we use to describe them. I also wanted to introduce this vocabulary word, isoelectronic, which means when you have 2 different atoms or ions, but they have the same electron configuration. So if you take a look at oxygen here, the oxygen ion has 8 valence electrons. On your periodic table, it has the same electron configuration as neon. They both have 10 electrons total, and they both have 8 valence electrons. So the word we use to describe those would be isoelectronic. So we like to take a moment to kind of organize all of the thoughts that we just had into a table. So that's what this is. So what we're going to do is we're going to determine what happens to these elements when they become ions. So the first thing we have to figure out is the total number of electrons. That's the same as the atomic number on the periodic table. So we have cesium. Cesium is number 55, so it has 55 electrons when it is an atom. Its valence configuration is 6s1. It only has 1 electron in the 6th energy level, so that's what's included in the valence configuration. So we have to figure out, are we going to gain electrons or are we going to lose? If you take a look at the groups, all the groups are going to do the same thing. Cesium is in group 1, just like sodium, potassium, and lithium. So what's going to happen is it's going to lose 1 electron. So I'm going to write L1. So what this means, I'm losing an electron, so my total number of electrons now is 54. And if you think about the charge, this is going to give me a charge of +1. My new valence configuration, I now no longer have any electrons in the 6th energy level, so I'm going to have the 5th completely full, so 5s2, 5p6, which gives me my total of 54. So this cesium is isoelectronic with something that has 54 electrons, which in this case is xenon. We're going to do the same thing for the next one. Chlorine has 17 electrons because it has its atomic number of 17. My valence configuration is going to be 3s2, 3p5. So instead of losing 1 like cesium did, chlorine is going to gain 1. So my new valence configuration with that additional electron is going to be 3s2, 3p6 for a total of 18 electrons. So chlorine's kind of doing the opposite here. So we're going to end up with a -1 charge. Remember, electrons have a -1 charge, so it's kind of the opposite of what you're doing. Also, keep in mind, if you take a look at the group 17, which is the halogens, they're all going to gain 1 to be like the noble gases. So the chlorine is going to be isoelectronic with argon. So why don't you take a moment to try the remaining 3 on your own. So pause the video and then come back. So here's what you should end up with for your first chart here with your charges. They all are following pretty much the same rules. So taking a look at this second chart, it's a bit different from what we had before, and this is similar to what we had in the atom unit. But what we're doing is we're determining protons, electrons, and neutrons, and the valence configuration for some ions or elements. So if you take a look at the ions or elements here, the way that you know something is an ion is that it has a charge. So all of them are ions except for barium. Barium is an atom at this point because it has a neutral charge. So the symbol, this is just like your symbol of your ions. So calcium has a +2 charge. So calcium with that +2 charge is still going to have 20 protons. We need to figure out the number of electrons. If you take the number of protons and subtract the number of electrons, that should equal your charge. So in this case, we need 18 electrons. The only thing that you can change when it comes to making a charge is the number of electrons. So we lose 2 electrons to give us the +2 charge. The number of neutrons, just like before, we take the mass number, which in this case is 40, and subtract the number of protons. So we'll end up with 20 here. And then the last step is writing the valence configuration. So keep in mind, because it is an ion, it's going to have be isoelectronic with the noble gas. In this case, it's going to be argon. So it's going to be 3s2, 3p6. So we're going to do the same thing for the remaining ones. Why don't you try it on your own, and then I'll show you what you should have. So here are the configurations, or the completed table. Hopefully yours matches. Notice for the one that's still an atom, my electron configuration only has, or my valence configuration only has 6s2, so it's not a full valence shell at that point. So up to this point, we've talked about the way following all of the rules set forth for writing an electron configuration. There are some exceptions to the rule for transition metals as well as the intertransition metals. So some of the configurations for the transition metals have exceptions just due to a potential lower energy configuration that's available for it. The intertransition metals have a lot of exceptions, but we're not really going to look at those because the pattern is much harder to recognize. You would be expected to know your electron exceptions for the transition metals, though. So for copper, the configuration that we would normally have following all the rules, I'm just going to do the noble gas shortcut here for it to make it a little bit quicker. So it would be argon, and then what we would do, we would have 4s2, 3d9. So that would be what you would expect to have. So I'm going to draw out the orbital diagram here as well. So 4s would have 2 electrons, and 3d, which has 5 orbitals in it, would have 9. So taking a look at this, we have a kind of open spot in 3D with everything else full. That would be what we would expect to have, but in actuality it's a bit different. Copper, we would have argon. It would become 4s1, 3d10. So if you wrote the full configuration for it, so starting from 1s, everything else would be the same except for the last s and d. So this ends up happening because it requires a lower amount of energy to have a partially filled 4s and a fully filled 3d. So your 3d is going to be completely filled, while your 4s is just partially filled. So this is just one of those things that ends up happening because of the difference in energies. So this doesn't only apply for copper, it also applies for silver and gold. Anytime that you're given copper, silver, or gold, you would end up writing the actual configuration here. So you would draw this if it were asking for the noble gas, or whatever configuration would be necessary for that. So it is a bit different from what we're used to. The second example here is with chromium. You still would have argon. It would end up, what you would expect to write would be 4s2, 3d4. In actuality, it's going to do something very similar to the one before. It's going to be argon, 4s1, 3d5. So again, we're moving one electron from the 4s to the 3d. Drawing our configurations here, it's going to look very similar. In the 3d with 4 electrons, we have one orbital that has nothing in it. So when we move that one electron over, we're going to be saving a significant amount of energy, which is why this ends up happening. So this happens for chromium, molybdenum, and tungsten. So those are the 3 elements that you would be responsible for those. So it's the 9th, or it's the 6th group on the periodic table for chromium, and then the 11th for copper and those respective groups. So both of these examples here would be considered the ground state, which is the normal resting state of electrons. We are going to talk about excited electrons. When electrons are excited, they have an excess of energy, and what ends up happening is they don't follow all of the rules set forth. So when we write it under normal circumstances following the rules governing electron configurations, it's referred to as being in its ground state. So just to reiterate, we have the Aufbau principle, which electrons enter the orbitals of the lowest energy first. Hund's rule, electrons enter orbitals of equal energy one at a time with parallel spins. And then the Pauli exclusion principle, no 2 electrons in the same atom can have the same 4 quantum numbers. Another way of looking at this is no 2 electrons in the same atom can be in the same orbital spinning in the same direction. So same orbital spinning, same direction. So in other words, you can't have 2 electrons spinning the same way in whatever orbital that you're working with. So one of the things we'll have to be able to do is identify, first of all, is it ground state or excited state? And then if something's violating the Pauli exclusion principle, that just can't happen in real life, so that's going to be an impossible configuration. So we have 3 possibilities. We could have an ground state, excited state, or it could be an impossible configuration. So I have some examples here. We're going to determine the impossible one first, because that's going to be the easiest one to identify. That's going to be the 3rd one here, because we have 2 electrons spinning in the same direction. So this is an impossible configuration. Because it's impossible, it's the Pauli exclusion principle, which I'm going to abbreviate PEP. So this is violating that rule. This electron configuration would never be able to exist. So again, the ground, if something's in the ground state, it's what we would normally write for the electron configuration. So if you take a look at the first one here, this is an expected electron configuration for something. So this would be in the ground state. If it's in its ground state, it's not going to be violating any rules. So in the second example here, we have 1 electron that's spinning opposite the other 2 in a p sublevel. So that electron is excited. So it has an excess of energy. So it's in its excited state, it's spinning in the opposite direction. So it will eventually return to its ground state where something else will happen. But this right at this moment is an excited electron. So this is violating Hund's rule. Hund's rule states that you have to add 1 electron to each orbital of the same sublevel before you pair. So then in the 4th example here, it's very similar. It's an excited electron because of Hund's rule. We have an electron in the D block spinning in the opposite direction. And then the last example here, we also have an excited electron. The S block was skipped, so this electron, the last electron added to the P block, should be in the S block. This is an excited state, and this is an Aufbau violation. So what you might be thinking, we just talked about electron exceptions. So what if you had something that could be the exceptions? Generally with these, you aren't always given what specific sublevel they're in. So if you had something, let's say you had 4s and then 3D. Because, so let's say we had copper. So we had this. So we had one electron in the 4s and then a completely filled 3D. Because this is an electron exception, this is copper, this is going to be the ground state. So there's going to be no violation here because this is the typical electron configuration for copper. So it's kind of odd to think about because if you had the traditional one for copper, this would be what you would expect to draw, but this is actually the excited state. So it's kind of odd when it comes to those electron exceptions. Even though this is technically excited, it's because it's not in its ground state. So the ground state for those exceptions are a bit tricky to think about. Because for copper's group and chromium's group, they violate when they're in their ground state.